noon. I'm going to talk about an idea which was proposed about 20 years ago. And you might say it's an old idea, and it is. And it hasn't found recognition in the community. Who knows, maybe it's wrong. My background is more in MHD jets and winds from disks and from pulsar magnetospheres. The reason this idea stayed for so long, after we proposed it with my collaborator Dimos Kazanas 20 years ago, then I left the field completely. I went to work in industry as a production engineer in aluminum rolling. And for 6, 7 years, I was away from astrophysics. Then at some point I returned, and there was not much interest in this idea except for a paper by Richard Lovelace and Bisnovati Kogan, who in some sense refuted the concept. So since then, we have done a lot of work with our collaborators in Athens and elsewhere in Europe, and we have observational confirmation that suggests that this might be an interesting idea. So I will repeat many things that Professor Blandford talked about previously, but I will give my own view of the problem. My feeling is that black hole magnetospheres and black hole jets have been investigated for a long time, and especially in the last 10 years or so, there have been so many numerical simulations, very difficult and hard simulations, that it seems that the community is reaching a consensus that we know the elements of these systems, a black hole, an accretion disk of a certain type around it, the whole thing threaded by magnetic field that somehow comes from large distances and is accumulated around the black hole horizon. And maybe this is the picture of the problem. I will discuss the several issues of this picture in a very simple framework, the basic concepts of them, how I understand the problem. So I will start with an introduction on black hole magnetospheres to show you the work we have done in the last 5 years or so. Then I will present this cosmic battery, and then I will end with those observations and the future of our work in the next few years, what we plan to do to work more on this concept. A disclaimer here, the title of the conference is Black Holes as Cosmic Batteries. I am not involved with the organizing committee of this conference, and this concept has nothing to do with the overall subject of the talk, which is black holes as, in a sense, energy accumulators. As Professor Blandford said before, they can deliver a lot of energy, about roughly 30% of MC squared, they can deliver that energy. So they are a very important source of energy at the centers of the galaxies for the supermassive type, and the smaller ones, the stellar mass black holes, can also produce a lot of energy. So the cosmic batteries, in the sense of the title of this conference, meaning engines, energy accumulators, or dynamos, or magnetic inductors, as we saw previously. Cosmic battery in my talk is a different thing, is a particular physical mechanism that tries to account for how the magnetic field is generated. So let's start with a few images. This is an image of this famous galaxy M87 in the Virgo cluster. You see the galaxy is quite large. It's tens of thousands of light years, the size of the galaxy. And at the center, very close to the core of the galaxy, you see this bright feature sticking out. This is the jet of M87, but it's rather small. The whole structure that we saw in the previous talk ends inside the galaxy, doesn't extend beyond the galaxy. So this is an optical image, but there are images in the radio with VLBI techniques, and we can approach close to the origin of this jet, a black hole, a supermassive black hole of several billion solar masses, and we hope that in the near future we will maybe be able to even observe the region near the horizon of the black hole itself. One thing that was mentioned before was that this jet that we see at large scales of a few kiloparsecs, a few thousands of light years, is edge brightened. It's like a sheath of radiation. It's not filled with radiation. What we see comes from the edge of that jet. And that jet has a parabolic shape. I will show a formula in a couple of slides. And then after about 100 parsecs distance from the center, it becomes conical. So this is roughly what we know, that it's a sheath emission. It's radiation coming from the boundary of that jet. There have been very recent observations in the last, let's say, since 2012, the last 6 years. Assad and Nakamura have been trying to publish this picture. They have been announcing their results for years in conferences, but the first time we saw something published was in this paper in Astrophysical Journal, where they talk about one extra component in this jet. They talk about a spine jet. So the sheath is emission coming from the boundary of that thing, but there is also something coming, a distinct component, which is coming along the axis of this object. And this component has its own kinematics and its own shape, and there are other people who claim that they can even follow motion of different pieces and parts of this jet. We heard previously about helical motions in the well-known sheath jet, and we do observe them, but it seems that we also observe things moving around along this spine jet. And these are their results. Here we see the size, the radius of the jet, and this is the distance from the core. And as we move out, the sheath component has a certain collimation, a parabolic type, but the exponent is 1.7. So it has a shape like a parabola with an exponent 1.7. This extra spine component is collimating faster with distance with an exponent r square. And they seem to be distinct. So who knows, maybe this is associated with the leptonic jet from the black hole, and we will talk about that again. Another thing that is interesting with those jets is that we can, it's a hard business, this field, but we can get Faraday rotation measurements at large distances of these jets. Faraday rotation essentially tells you, well, very quickly, it tells you the direction of the magnetic field along the line of sight that you're observing it. So very roughly in this picture here, red is positive, meaning that in this part of the jet here, which is again plotted again here, in this part of the jet, the origin of the jet, there are parts where the magnetic field is pointing towards you, and on the other side of the jet, the blue color is negative, the magnetic field is going away from you. So you might think that, and there are measurements of this gradient of the Faraday rotation from positive continuously to negative values that show across the jet, in this picture here and in this picture here, that show the magnetic field changing from one direction to the other. And this is suggestive of a helical structure, of a toroidal structure of the magnetic field around the jet, which suggests that the jet is threaded by an electric current that moves out. But before we get to the electric current and our cosmic battery, the interesting thing is that this jet on kiloparsec scale can produce Faraday rotation associated with the jet. Well, it can be from something that lies between us and the jet. But when we see gradients from one side to the other continuous like this, we think that those gradients are associated with the magnetic field of the jet itself, or probably in the vicinity, probably in the wind around the jet. So this means that if they can produce Faraday rotation, this means that at large scales, those jets are not leptonic, and they consist of ordinary plasma, electrons and protons. An electron-positron plasma does not give you Faraday rotation. Then we have this other variety of jet, the small scale ones, the ones from X-ray binary objects where a black hole, or even a neutron star, but black holes are more interesting, where a black hole goes around the star and sucks the matter of the star and forms a disk and forms a jet. And there are these well-known objects, Cygnus X1, GRS 1915, SS 443. And those objects produce jets, and those jets, especially in this case, this is the famous microquasar discovered and observed by Felix Mirabel, and those jets are very dynamic. They produce those blobs that move away superluminally, and you see one blob moves up, the other moves down. We can follow them over months, over years. So we think that these objects in which we can follow the evolution much faster than their cousins, the supermassive black hole ones, we think that they are, let's say, they are cousins of the same, they are part of the same family. What applies in the stellar size jets and black holes, similar, we can get similar conclusions for active galactic nuclei in supermassive black hole jets. So let me start with an introduction of what we know, at least what I know, at least what I'm trying to learn about black hole magnetospheres. And remember that my background is from pulsar magnetospheres, and I will try to convince you that black hole magnetospheres and pulsar magnetospheres are very, very similar. We can learn a lot of things from pulsars and apply them in black holes, and in some sense the black hole magnetospheres are simpler than the pulsar ones. So this is a work we did with my student Antonios Nathanael a few years ago. So when we study black hole magnetospheres, we assume that the conditions are so-called force-free and ideal. We saw the equations previously, I will not repeat them, but the idea is that the total electromagnetic force on the plasma, so electrostatic force, electric density times the electric field plus the Lorentz force J cross B, that total electromagnetic force in this charged plasma, which is threaded by electric currents, that force is equal to 0. And you can rewrite the problem and you can get the electric fields, and this whole analysis is done in axisymmetry and also steady state, and I will show you solutions. But one thing to remember, and please do remember that when you leave this, when I'm done with my talk, is that black hole magnetospheres, they naturally develop electric current sheets. Not only electric currents flow in the magnetosphere, but it's an unavoidable result that they also develop along the boundary of the jet. They develop electric current sheets, very narrow regions with a lot of electric current. And I will tell you why in a minute. So this previous equation, the force balance equation, if you express everything in terms of the magnetic flux, and it's done here, then you get a big equation which is like a Grad-Shafranov equation in the force-free ideal limit, which is something like a generalized pulsar equation. That's not important. One thing that you should remember is that this equation is second order. Again, it's steady state and axisymmetric. It is second order in the spatial coordinates, so it's an elliptic equation. But what is most important to remember is that this second order part of the equation, which is the important part if you want to solve this equation, this is multiplied by an expression which may become 0, being positive, negative, it can change sign. So this equation is a singular equation. It's not an ordinary elliptic equation that you can go on and solve it easily. The same equation in a simpler form applies in pulsars. As I said, pulsars are more complex, and you will see why, but the equation that describes pulsars is simpler, and that singularity, that term there, gives you the so-called light cylinder. It means that if you have a magnetic field line that threads the stellar surface and extends very far away, and that magnetic field line, as we heard previously, correlates with the star, there is a distance from the star where that velocity of co-rotation becomes equal to the speed of light. This light cylinder singularity appears as the term that multiplies the second-order spatial terms of the elliptic equation in pulsars. The same thing applies in black hole magnetospheres, only now it's a little bit more complicated because space-time itself, the natural observers, they're not standing still, they're also moving around, and this description is obtained with respect not to static observers, but with observers that go around with some omega of the space-time. These are the Samos, zero angular momentum observers. And you can imagine that if a field line goes from the horizon to large distances, again, there is a distance if you go with that field line, and if you go around with that field line at about 1/2 of the angular velocity of the black hole, as we heard previously, which is roughly the velocity of rotation of that field line. If you are far away, then again, you will find yourself in a situation where you're moving very fast, but your observer now is also moving very slowly, and then you're moving forward with the speed of light with respect to the slowly moving observer, the Samos observer, at that distance. But now there is a second possibility, and the second possibility arises very close to the horizon, where now your omega is the same, the distance is much closer, so now you, the observer along the magnetic field, goes around slowly, but your observers move so fast that now with respect to those observers, you're moving backwards at the speed of light. So this results in two light cylinders or light surfaces because they don't look exactly like cylinders. The outer light surface and an inner light surface near the horizon. And what is interesting now is that if you want to solve this problem, you have to make sure that your magnetic field crosses those two singular surfaces smoothly without discontinuities and breaks. But how can you do that? In pulsars, we fix the rotation of the magnetosphere, which is equal to the rotation of the star. Everything is tied to the star. But in the black hole, we cannot really do that. Black hole is empty space. Nothing is fixed on a black hole. Black hole is just vacuum. The horizon is just vacuum. So there is a function of the rotation of the magnetic field lines, and every field line has its own angular velocity, let's say. That's one free function. Previously it was fixed in the pulsars. And the second free function is the same as one we had in pulsars, which is the electric current that goes through the magnetosphere. Two free functions, two singular conditions to satisfy crossing of the two light cylinders, and that makes your problem an eigenfunction problem, and you get the solution for the rotation of the field lines and the current in the magnetosphere as an eigensolution. You're not free to specify how fast the field lines rotate. You're not free to specify what is the current distribution. This comes as a solution of this eigenfunction problem. These are like eigenfunctions. And when you do that, you get the current that threads the field lines that cross the black hole horizon. And if you do that calculation, and I'm not showing the results, then you get a certain current that is distributed along the field lines, and you get to the last field line that crosses the horizon, and there is a finite amount of electric current that is contained in your jet, in your magnetosphere. Obviously, this cannot be the final answer. You have a current, and that current has to close, and the closure happens in a current sheet along the last, just outside the last open field lines. So we found the same thing in pulsars. As I said, black holes are simpler because pulsars have also this region of closed field lines, the co-rotating dead zone, as it is called, that reaches the light cylinder. Black holes don't have that. You cannot have field lines that cross twice the horizon. If you do that, then the field line will be detached and will escape at the speed of light. So these are the types of results we get, which are the same as Roger Blanford knew 40 years ago. And actually, he studied the split monopole problem, and other people before us, they imposed different shapes for that boundary, meaning that you have the black hole, you have something that is holding your field lines that are accumulated there, and in all cases we obtain a distribution of angular velocities in the jet and a distribution of electric current, and in all cases there is a singular return current along right outside the last open field line. In this picture you see the ergosphere. This is very fast moving black hole. This is the ergosphere, this is the light cylinder or outer light surface, and the red line is the inner light surface. And if you look at those plots, we have, through some iteration, we have tried our best to make field lines cross smoothly the inner and the outer light surface. So this is something that we learned, that black holes are similar to pulsars. There is a distribution of charge in the magnetosphere, and there is a region above the horizon at about 2m where the so-called Goldrake-Julian space charge goes to 0. This is the null surface. Outside of that it's negative, inside of that it's positive, assuming that the rotation is along the direction of the magnetic field along the axis. One thing to remember, which is not emphasized in studies of this problem, is that the current sheet itself, as I said, there is a current through the magnetosphere from these outflowing electrons and inflowing positrons, if those are produced here. But the current sheet, the return current, this big red arrow, the current sheet is also charged positively and negatively inside. And if one tries to solve the problem, where do the charges appear, then he or she has to also solve the problem. It's a more pressing problem. How do you solve? Where do the charges in the current sheet come from? Well, one might invoke the presence of the outside medium. So if that region there is not actually going out, like in the pulsar magnetosphere, beyond the light cylinder, but is coming up, then there is material, there is plasma, and probably that plasma feeds the particles that are needed in the current sheet. So these are interesting problems to study, and I saw a poster downstairs, and people like Amir Levinson are really getting into it, how the pairs are produced, by which mechanism. And there's another problem, that even if you produce the electrons and the positrons, those electrons need to escape the system, and we know that there is some surface at some distance inside which nothing can escape. It's like a stagnation surface, so even those electrons move out, they will return back. So there are discussions about the size of this gap to extend beyond the stagnation surface. But it's a very interesting problem. Other people like Ksenia Ptitsina and Neronov, they are discussing radiation produced by those pairs. So we really need to address those problems. It's not just a simulation, it's behind the simulation we need to ask ourselves and answer the question, what is the origin of the charges that we need? If you have no charges, nothing of that works. It's like a vacuum. You just have electric and magnetic fields, no currents, no charges. You need to produce charges to make this black hole, to make it a magnetosphere, and to make it, extract and to make it an engine. Without charges, it's a dead pulsar. It's a dead spinning black hole. So there are many, many problems that somehow will be solved in the future. So if there is a current sheet, we can think that there's probably particle acceleration in the current sheet if there is some kind of reconnection, and also that may be also a wind, the particles that are accelerated in the current sheet. So the kiloparsec scale jet that we observe is not the electron-positron jet from the black hole, so either it is a disk wind, and we're seeing the inner part of the disk, and that disk is probably radiatively inefficient, has a lot of mass, but we don't see it radiating, but there is outflow, electromagnetic outflow by the magnetic field, and probably so the jet may be the innermost part of that disk wind, or it could be particles accelerated in the current sheet, or another solution that is popular is that probably it is loaded with stellar winds, and gradually from electron-positron dominated, it's loaded with ordinary plasma. Okay, these are roughly the things I know and I'm trying to learn and understand. And it's not a lot. I'm sure people in this room know much more than I do. But there is one thing that has been very interesting to me, as I said, 20 years ago, and it still is. What is the origin of the magnetic field? To make a Faraday disk spin down, to extract energy in an electric motor, to light the light in your bicycle, all these unipolar inductors, as we say, and the black hole is one type of unipolar inductor. To get energy out, yes, you need the charges to close the circuit. You need charges. Without a circuit, an electric circuit, you do nothing. But first of all, you need the magnetic field. So where does the magnetic field come from? So the standard picture is that the magnetic field is somehow generated far away, and accretion brings the field in. But then there are these discussions that probably accretion, because it is accreting and the matter and the disk is losing angular momentum, and because there is MRI, probably the accretion disk is very turbulent. I'm sure it is very, very turbulent. But if the disk is very turbulent, then it's also magnetically diffusive. Which means that if it's magnetically diffusing, it cannot really hold on the magnetic field and bring it to the black hole where you need it to start this engine. So probably the accretion process is very inefficient. Probably it works, probably it doesn't work. Even numerical simulations where they have the field, the reservoir of field at large distance, and they bring it in, even those simulations attain some numerical diffusivity in the disk. I will show our simulations where there certainly is numerical diffusivity, and there certainly is some escape of the field from inside out. So what is the origin of the diffusion in the disk? These are big questions. One answer, I'm not saying it's the only answer, but one answer may be that the magnetic field it's generated through radiation. And now I'm going to present you this idea that we have in the literature, and we're trying to advertise it in the last 20 years. The cosmic battery in the black hole magnetosphere. And the idea is the following. You have plasma around the black hole, and there is a lot of radiation there. We see the system radiating. And, well, the radiation comes from the matter itself. The matter is hot and radiates. So if you are a particle, or if you're an electron, if you're an observer going around with a disk, and assume this very simple models, these are simulations with ray tracing. We trace the radiation, the photon rays. In this, we have assumed a thick torus around the black hole. So the black hole is somewhere here, and it doesn't show very well. So the black hole is somewhere here, and we're sitting inside this torus, and we're going around with the Keplerian rotation of the torus. So it's everywhere hot, and radiation comes from everywhere, from behind, from above, from the side, from the other side, and we calculate those rays. But in the end, because we are moving, if I am sitting in the frame of the plasma that goes around the Keplerian rotation, because I am moving with respect to this more or less isotropic magnetic field, I am seeing radiation hitting me opposite to the direction I'm moving. Now we can play this game and change the position of our observer, and we can bring the observer closer. Then we see something like this. These are photon orbits that make it around the black hole. I think they're called light circles, so on. If we are even closer, this part is radiation that comes from behind. Now space-time is also rotating. This is a fast rotating black hole. So photons reach us not only from this part, but they can also reach us around the black hole and reach us from behind. So this is our back, this is our front. And if we are even inside 3m, the radiation from the photon that reaches us from behind becomes stronger than the radiation of the photons that reach us from the front. And you can imagine that this radiation pressure, in this case, it is trying to decelerate our electrons. In this case, it tries to accelerate our electrons. And if we're even closer at the inner edge of this accretion disk around the maximum, this fast rotating black holes, most of the radiation comes from behind. The photons go around the black hole and essentially hit us from the back and push us and accelerate us. So let's get back to the previous picture, and let's assume that the source of photons comes from the center. If the photons are isotropic, and I'm doing this now non-GR classically, if the photons come from the center, there is a radiation pressure from this luminosity, and this is the force, the radial force. This part here is the Eddington pressure. It's the radial force on the electrons of the plasma from a point source at the center. This force here is the radial force outwards. But because we're moving with some Keplerian velocity, this force is aberrated, as we say, in the azimuthal direction. And what this radiation force does, it tries to slow down the electrons. The protons don't feel that force. The cross-section for the protons is the ratio of the mass is square. It's negligible. So the electrons are slowed down in the plasma as it moves around the black hole. By the way, this effect is well known and has been observed in the solar system, not on electrons, but on dust grains that go around the sun. So dust grains have their own cross-section, they have a size, they collect photons that come from the sun, but because they are moving with Keplerian velocity, they are slowed down in their rotation. And as a result of that slowing down, grains that are produced from collisions of asteroids between Mars and Jupiter, let's say, then those grains gradually drift to the inner part of the solar system and generate what we observe as zodiac light. It's a real effect. The grains are slowed down. We are proposing that electrons are also slowed down. But let me backtrack a little bit and say, so there is a radiation force on the electrons that is felt by the electrons that opposes the motion of the electrons, but not the protons. But let me backtrack a little bit. When there is a radiation force, in all cases, the radiation force is calculated in the frame of the plasma. Because in some sense, you can see this effect that the electrons absorb the radiation and re-emit it isotropically, and that's how the momentum is transferred, and you have to do the calculation in the frame of the plasma. But so there are codes that calculate the radiation force, and that radiation force is included in the momentum equation for the protons. So the protons feel the radiation force. This is very basic in astrophysics. There's radiation, the plasma, which is the protons, the ions, they feel the radiation force. But how is that possible? The radiation force is felt by the electrons. We just said that the radiation force is felt by the electrons. How is the radiation force transferred into the plasma, the bulk of the plasma? And the way this is done is people write the equation of motion for the electrons. The electrons feel the radiation force, but because of the radiation force on the electrons and not to the protons, there is a shift between the positions of this electron cloud around protons, and essentially an electric field appears. And the charge of the electron is negative, so the equation of motion of the electrons includes now an electric field. But if there's an electric field, now the protons, they can feel the electric field, but with a plus sign here. And then what we say that the first equation, because electrons and protons essentially move at the same velocity, and they are not accelerated too much, so essentially because the mass here is very, very small, essentially this equation gives you roughly 0. From which, from the first equation, you get the electric field that develops in your plasma because of radiation is the radiation force divided by the charge, the positive charge of the electron or the proton. So the electric field that develops is along the direction of the force. So if I am moving, the electric field is roughly opposite to the direction of the motion. And this is how the radiation force is transferred to the protons, and then we forget about the electric field. So all the codes that have radiation, like harm with radiation or coral with radiation, this is how they transfer the radiation force to the plasma. But if you want to really follow the physics, the fact that your plasma consists of electrons and protons, not electrons and positrons. If it's an ordinary plasma, then you have to remember that there is an electric field in your equations. And that electric field appears also in the induction equation. It is a term that is very small and appears in the induction equation. And in principle, you have to take into account and gives you very interesting results. So let me show you something that everybody understands. The second part in the accretion disk, people debated, but I don't think we should. But anyway, if we have a star and there's radiation coming from the central part of the star, like our sun, it's very hot, and that radiation pressure really holds the star. I mean, without radiation pressure, stars would collapse. So that radiation pressure comes from the center and goes out like this. These are photons that travel through the sun, but roughly on average they move out. They take 1 million years to travel out, but they come from the center and they move out. So they're pushing on the electrons, but not on the protons. So how does the plasma feel the radiation pressure? Well, by pushing on the electrons, those electrons are accumulated more in the outer layers or along the surface of the star, and because by doing that, they are depleted from the center. So it's obvious that inside stars, there is an electrostatic electric field, which means that if I take my voltmeter, I can go and stick one pole to the center, and the other to the surface, and I will get a voltage measurement. I haven't done this calculation, but there's some voltage measurement between the center and the surface of the star. And this is the electric field due to that voltage, and that electric field is holding the protons, and this is how radiation pressure affects the plasma, the bulk of the plasma. So the next thing is that we do the same thing, we can do the same thing in an accretion disk. So now it's not a star, it's an accretion disk. It goes around in a certain direction around the central black hole. And I will assume there is a sort of source of radiation here, but in reality, the source of the radiation is the disk itself. So I will play the same game to make it simple. And I will assume that those photons that come from the center reach a certain depth in the disk. There is an optical depth up to which they can travel. So all along this travel of the photons through the disk, they're pushing on the electrons, but not on the protons. As I said, the disk is rotating, so it becomes charged, more negatively here, more positively there. There is certainly a radial component in the electric field, but because of the rotation and because of the aberration, and as I said, the force is slowing down my plasma, slowing down my electrons, you develop also an electric field in the azimuthal direction, and that is the electric field of our cosmic battery. It's not correct to say that the protons move around and the electrons are held back, so there is a difference in velocities between the two, so there is a current and there is a magnetic field. This is not the correct way to see this effect. You cannot just turn on electric currents in a plasma. In the solar corona, you cannot just turn an electric current in one of these active regions. You cannot do that. The plasma will react. It's safer to study the phenomenon through the electric field that appears in the plasma. So now, this azimuthal electric field opposite the direction of rotation, if you check what happens here and what happens here, there is no field outside. There is some azimuthal field here, and there is obviously a curl of the azimuthal electric field here. Similarly here, there is an electric field here. There is no electric field here, either because the plasma is freely falling radially in, or radiation is not important, I don't know. So there is also a curl in that direction. So a curl here, a curl there. There's a distributed curl. Take the minus sign of that curl, put it in the induction equation, and so there is a curl of the electric field. And if you do this calculation in your mind, you start growing the field in this direction out here and in this direction in here. Let me show you the induction equation again. Our source is in the azimuthal direction. I take the curl of that, I put a minus sign, and that gives me the rate of growth of the field out of the plane of the disk. And it is coming out where the black hole is, going down through the disk at larger distances. So these are loops of magnetic field above and below the disk. It's like as if I had an azimuthal electric current. But as I said, we're not doing the calculation through the electric current. We're doing it through the electric field. So, and then what? If you have an accretion disk and you have accretion, there is an advection. Forget about the diffusion for the moment, assuming that the plasma is ideal. And you only have rotation plus accretion. So you generate some magnetic field. Essentially, you're generating loops out of the plane of the disk and back through the plane of the disk. And then, if you have no diffusion, you generate those loops for some time, magnetic field up, magnetic field down, and the whole thing is advected and accreted and enters the black hole. +1, -1 gives you nothing. So if I have no diffusion and I only have an ideal plasma that advects everything, then the mechanism, if you do it a little bit more carefully, the mechanism within one or a few free-fall time scales, the mechanism saturates. And you generate some magnetic field, but that's it. The magnetic field does not grow continuously. You might say that because I have this term here, if I knew nothing about the other terms, that term, the curl of that term with a minus sign would give me a continuous growth of the field. This is not correct because I have an accretion flow, and the accretion flow will take my loop, put it in the black hole, and then I don't gain anything. +1, -1, the result is roughly 0. So this was the criticism by Lovelace and Bisnovati, Kogan, and Belinsky a few years ago. Our model has one more element. So there is a source of the magnetic field, which is the electric field. And there is, from the very beginning, we understood that you need one more element. And what you need is the separation of advection to the center from diffusion through the disk. You need also the diffusing part. So what happens, what we think happens, is that you generate those loops of magnetic field going out and back in the disk. That part here, it's very close to the horizon, is advected and increases the magnetic field of the black hole. If I were to bring in the return polarity, then I would have done nothing. So on one hand, I need to accrete, and on the other hand, I need this part here to diffuse outwards through the disk. In reality, what happens, those loops, because of differential rotation, are twisted, they're open up, so they become essentially lines that go out and lines that come in here, and those lines slowly diffuse outwards, and the process keeps repeating and repeating and repeating, and we get a steady growth of the flux accumulated on the horizon. So the result is that there is a magnetic field along omega around the black hole, and there is a magnetic field opposite to omega in the disk surrounding the black hole. So again, I emphasize that it's not only the source, the electric field source, the curl of which is non-zero. It's also, this is a constituent, let's say, of the mechanism we are proposing. We have proposed that since the first paper. You need an ideal inner accretion disk and a diffusive outer disk for the mechanism to work. Okay, over the years we have done our own simple 1D. The original paper was a 1D simulation, non-GR. and we did some non-GR simulations in 2D with our collaborators, and we essentially reproduced what we knew in the original paper. But at some point, we collaborated with Oleg Sadovsky, former students of Ramesh Narayan, and we used, actually he did the simulations for us, he used his code Coral with radiation in GR, and we tried to simulate our effect. So what we did, and this was new for us but not for the community, Coral is following, it has a mass conservation equation, it has an energy momentum equation which would be 0, but there's also an energy momentum tensor for the photon field, and that gives a certain force, and that force from the photons is transferred to the plasma. So this is not 0, this is not 0. There is a remaining radiation force that is taken from the radiation field and it pushes onto the plasma. This is essentially the force the electron feels in its frame. Actually, the force that the electron feels is the projection of that force, the radiation force density, as they call it, the projection of that in the frame of the plasma. And that's why the velocity of the plasma enters here. So this is something known. It's nothing new. This is in the equations. What was new in this paper is that we took this term here, translated it into an electric field, and added it in the induction equation. This is dB/dt, and it has an extra term. As you can see, the code is ideal, so it's only a V cross B term here. There is no diffusion term. So in principle, as we have predicted, the battery, the cosmic battery, our cosmic battery should not work. So again, it's a modified induction equation. By the way, the presence of that term is not something new. We know this is taken from Wikipedia. I took it last night. This term here is just the pressure felt on the electrons, generates an electric field, and is included in the induction equation in the Biermann battery mechanism. There's no question if it has a curl, if it's the curl is 0, it's non-zero. It's a non-zero curl and gives rise to magnetic fields. This term exists, has been used in the literature in the induction equation, in the Biermann battery. This is the work of Bisnovati, Kogan, Lovelace, and Belinsky that criticized our work. It didn't criticize the presence of the electric field. They have the same electric field due to radiation that we have in our paper, actually in more general form in the paper with Sadovsky. So the field is there, the curl is non-zero, here is the curl, and this curl acts as a source of the magnetic field. Of course, if you do that in ideal regime, that gives you saturation. So what did the simulations give us? Okay, there are tricks to do the simulations. Well, if you are interested, I will describe that. So this is what Oleg decided to do. The time scale TG is GM over C square. Okay. So the dynamical time at the inner edge of the disk, and we evolved that for tens of thousands of dynamical times. And what we get is that the field reaches a steady configuration. We started with a configuration where the field was up and down in the flow. So there was initially there is no preferred direction of the magnetic field. So on average, there is no flux accumulation on the black hole. The flux in the black hole just evolves up and down around a certain non-zero value. But overall, you develop a so-called standard and normal evolution. There's no growth of magnetic field in the black hole. And at that time, 22,000 dynamical times, we switched on the new term in the equation. And to do that in a finite amount of time, we increase it by several orders of magnitude, because as I said, it's a very small term. And what happens is you start building the field, more and more, and at some point the field that is built around the black hole becomes so strong that the accretion stops. The accretion on the horizon, right outside the horizon. So this is what we call a magnetically arrested disk. And it's 2D and cannot evolve beyond that point because you need the third direction, in the phi direction, for matter to accumulate. But what we obtained without asking for it, we have one polarity, B along omega, growing around the black hole, growing almost linearly, as you will see, but the return polarity gradually moves out and sweeps everything through the disk. The reason it moves out is just numerical diffusivity. We have no control on the diffusion of the return polarity through the disk. It just appears. We were lucky that the simulation was diffusive enough to show the effect. And this is the flux accumulated around the black hole after about 20,000 dynamical times, and you see nothing, but then gradually you see this linear growth at roughly the rate that we predicted with the cosmic battery. And at some point, accretion stops, and we stop the simulation. Okay, not because of this numerical simulation. We know it is artificial. There are many things. We can do it in 3D, but it's very hard to do it with realistic values of the electric field. We had to increase it, but there probably are ways to do it even for realistic values. I mean, run simulations for some time and then advance the simulation forward in time and run again a detailed simulation. So we're thinking of ways of doing it more sophisticated, but I don't think we will learn anything beyond what we knew 20 years ago. So do we see any of that? I have roughly 10 minutes to finish this. So do we see any of that? For example, do we see that the magnetic field is along omega near the black hole? Well, when we, a few years ago, Donald Lindenbell came to Athens to a small workshop we had organized. He became very interested in that idea. He went back to Cambridge and he said, okay, let's look for galaxies that are face-on, spiral galaxies, in which, because of the direction of the spirals, you can tell roughly the direction of rotation of the galaxy. So this galaxy, for example, is rotating clockwise. And there are others that rotate counterclockwise. And he also looked for galaxies with rotation measurements in the innermost at the core. And he said, okay, I have the rotation measure. I know the direction of rotation. I can put them in a plot. Direction of rotation, clockwise, like this galaxy. Anti-clockwise, like the mirror image of this galaxy. And he found 9 cases in the literature, not looking too hard. This is just a short letter in Cambridge. It's not a real paper. And he looked for the Faraday rotation at the innermost part of those galaxies. And he put them in a plot like this. So clockwise, rotation measure negative means the field goes in the board. Anti-clockwise, rotation measure positive means the field comes out of the board. Except for this example here, and probably this is very, well, one counterexample. All the other 8 examples follow this rule that B and omega are along the same direction. He called that magnetism along spin, and this is certainly something that cannot be explained with MHD. MHD doesn't differentiate between the 2 polarities of the magnetic field. We were more interested in the twisting of the field. And this is interesting. If the field is, if the direction of rotation is like this, let's look, for example, for the field in the inner part that threads the horizon. The field is along omega, goes out. So BZ is out. But because now you are spinning the foot point, then you wind it and you generate this winding of the field in this direction. Now imagine, the exact opposite happens for the field in the disk. Now imagine that you have the opposite case, that you're observing a source that is rotating in the opposite direction. If it's rotating in the opposite direction, omega is opposite, BZ is opposite, but now omega is opposite, axial field is opposite, you twist it in the opposite direction and you get the same direction, like this, the same direction of winding of the azimuthal magnetic field. So in all cases, this mechanism proposes that the winding is, let's say, is in the same direction. Essentially what this means, it means that the electric current through the system regarding the black hole jet is always going to the black hole from both directions, to the black hole, and regarding the disk wind, it's going out from the black hole, in all cases. So what do the observations tell us? Observations tell us this was apparently the discovery of the highest electric current in the universe, 10 to the 18 amperes. Again, my former advisor, Richard Lovelace, with Philip Kronberg, they were involved in this paper. And if you look at the maps of Faraday rotation, the current that they observed moves from the core out along the jet. And we looked up in the literature, M87 has the same thing. You see, the field goes like this, the current is out. And there are this region here, for example, this region there, I don't know how much you believe those, but the current is out. And there are patchy regions where you cannot really tell if there's a direction of the electric current. Again, this 3C303 was the Kronberg paper. There's a gradient there, the current is out. Again, current is out, another example. Even in our own galaxy, if you look at background radio polarized sources and you do the map, you see that northern hemisphere, southern hemisphere of our own galaxy, again, the field corresponds to a current that goes out to the north, out in the south, in our own galaxy. So we looked up all the cases of jets with Faraday rotation measures in large scales, and we could detect consistent gradients across the jet in 18 cases. In the other cases, all the measurements were very patchy. We did our best to find, helical fields. We couldn't determine them. But in the 18 cases where we could say that some part of the jet has a helical field, in all cases, the helicity, let's say, of the field corresponds to an electric current moving away from the core. And that corresponds to the field in the disk. So probably what we're seeing is emission from the jet going through the magnetic field in the surrounding disk. And this is wound in that configuration according to the cosmic battery. Let me finish. As I said, I advertised that we plan to do work on X-ray binaries. These are the small cousins of AGN jets, of these big jets. And this is an example of a micro jet, let's say. There's a lot of phenomenology in X-ray binaries. In X-rays, in radio, there are diagrams, many, many observations. There is not a consistent picture connecting everything. And what we see is that we see outbursts in the X-rays. I mean, the object becomes bright over 1 year, let's say, and then it dies again. And the spectrum of the object changes, and you generate those so-called Q diagrams, hardness intensity diagrams, and there is no really a model behind them. Why there is a jet, and then that jet disappears, becomes so episodic, and generates those microquasars that we saw before, and then there is no jet, and it comes back, and as it comes back, a new jet, a radio emission appears. Radio and jet are roughly the same thing in this discussion. Another thing that is very interesting, it's very recent, a very recent result by Kilafis and Raig, Pablo Raig, is that they are doing Comptonization in this corona in the inner part of this accreting system, and they measure time lags between high energy and lower energy X-rays. And from the time lag, they can estimate the size of that Comptonization region. And what they observe is that as the system approaches the intermediate state and there is a jet, and then the jet is destroyed, the size of that Comptonization region grows to about a few hundred, about roughly 1,000 gravitational radii, and right before you approach the point of the destruction of the radio jet, the size decreases again. This is the conclusion from their paper. And we think that this may have something to do with the battery. This is a cartoon from the work of Ferreira and collaborators, and they talk about a magnetic field threading the disk, and accretion pushes that field more and more and more, and at some point, that field is destroyed, and the emission becomes very dynamic and episodic, and you have these microquasars, these blobs that move out. Well, it is impossible to get rid of a magnetic field. It is impossible to. The magnetic field, you cannot make the flux disappear. If the field is in one direction, you cannot just switch it off. This is impossible. The only way to get rid of the field and generate something, and get rid of it, and then no radio emission, no jet, nothing, the only way to do that is if you have one polarity of the field here, and here it is not shown here, the other polarity on the disk, and if the conditions in the disk change, and all the field that threads the disk is brought in near the black hole, then you have the possibility of detaching the field and get rid of it, and then get to the soft state with no radio emission and no jet. And by the way, the time scale to return from the soft state to the hard state, which is weeks or months, well, that depends on the luminosity and all that, the time scales are very, very compatible with the time scales needed for the cosmic battery to regenerate the magnetic field and reform jets and reproduce radio emission. So this is work in progress. We hope that we will be able to continue it, and I will leave you with our picture of the system. Black hole pair formation above the horizon. I don't know how much of that is observable. There are current sheets that may also accelerate particles. According to the cosmic battery, they accelerate protons, not antiprotons. They accelerate positive particles. The electric field is in such a direction to accelerate positive particles. The field in the disk is closing in the disk. There is a current sheet. Because of this diffusion, there is a lot of flux accumulated in the black hole, which is held by the accretion flow, but there is a region empty of magnetic flux because we think that the field escapes through the disk. So this is the picture we have in mind. I think it's different in certain respects from the standard picture of the numerical simulations. And with this, I would like to thank you all for your attention.